So valence electrons. I'll read that once again. Welcome back to Chemistry in the AM. Mr. Shidelka. Valence electrons are the electrons in the outermost s and p orbitals. Non-metals, valence electrons tend to be the ones involved in chemical bonding. So they're the ones involved in the chemistry that we're going to study. Now, sorry, I want you to jot this down. Now, Te is tellurium. It's number 52 on your periodic table, probably number 1 in our hearts, but I have it down. This is the diagram here with the shortcut. Krypton is the previous noble gas, 5s2, here, 4010, 5p4. I kind of put a diagram above just to, you don't need the diagram necessarily, but I included it there. I'll give you a minute to jot that down. Okay, I said a minute, it's probably less than that, but you've got this jotted down. And according to this, valence electrons are the electrons in an atom's outermost s and p orbitals. Now, if you use the shortcut, the only electrons you're showing is 5s2, 4010, 5p4. Those are the outermost electrons. And if we're saying only the s and p orbital electrons, these are the valence electrons. 2 from the s, 4 from the p. That's a total of 6 valence electrons. Okay? Now, I want to zip back. Remember I said the previous example, or the electron configuration examples, I said valence electrons as well, and we come back to it. Now we're going to get back to it. You ignore, when you count valence electrons, you ignore D's or F's. So, nitrogen. Well, there's nothing on its outer row. There's nothing but S and P's. So we have, I'm going to put VE for valence electrons. 5 valence electrons. In iodine, we don't count the D's. We just say, well, there's these S ones and these P ones, 2 plus 5. That's 7 valence electrons. Uranium, we won't actually be doing chemistry bonding and stuff with uranium, but there's only S electrons that are going to be counted. The F's are never counted. There's 2 valence electrons. Finally, chlorine. The S's and P's added together is 7 valence electrons. I'm going to point something out in a minute here on the periodic table, because there's a pattern of valence electrons. Here's what it is. Because the periodic table is organized, you know, with the S's here, and the P's here, so if you're looking for valence electrons, we tend to first of all only really worry about the non-metals. And these are, I guess it includes the, these are the non-metals. Hydrogen is the other non-metal. Hydrogen just has 1 electron, so just 1 valence electron. Helium has 2 valence electrons. After that, these are general principles. In the 13th column, there are 3 valence electrons. In the 14th column, we've got 4 valence electrons. In the 15th column, 5 valence electrons, like nitrogen we saw. In the 16th column, I think you see the pattern, there's 6 valence electrons. We did 2 from the 17th column, chlorine and iodine. They both had 7 valence electrons. Lastly, the 18th column, with the exception of helium, there's 8 valence electrons, complete shell for these guys. So whatever the column number is, take off the 10, you got the number of valence electrons. That's just a memory game, whatever, and that actually is the quickest way to do it. But you got to understand where it comes from. And it's this S and P up here, okay? I'll pause for a second. Now we're going to look into how to do the actual Lewis diagrams using valence electrons. Lewis diagrams show an atom's valence electrons. They are easy to use than Bohr diagrams. Okay? Just jot that down, I'll give you a 30-second phosphorus. Now the way we used to do Bohr diagrams, I'll take a look at phosphorus here. You can now see how it's all connected to electron configuration. Here's phosphorus. So it's going to use 3 rings, third row. 2 electrons, 8 electrons across the second, and then 1, 2, 3, 4, 5 on the third ring of the Bohr diagram. We now understand the S's and P's, but we'll just talk about that. So, 2 for the first. I want you to group them in pairs. 8 across the second. 1, 2, 3, 4, then double them up. 5, 6, 7, 8. After they're all singles, you can double them up. And then 5 on the third ring, the third row, to get to phosphorus. We now understand that they're really S's followed by P's. So 1, 2, 3, 4. And the fifth one is double them. So that's what we used to do. You do still need to understand that. But we now realize in chemistry it's the outermost S and P electrons that we're going to be worried about with chemical reactions. So all you really want to do is take the outer ring electrons, these ones. And you don't, sorry I didn't mean to expand that. Anyways, those are the electrons we're going to put on the Lewis diagram. It's just a Bohr diagram showing only the outermost and no ring. So we go 1, 2, 3, 4, 5. That's how you do a Lewis diagram. And remember how I was saying? 15, 5 valence electrons for phosphorus. I'm going to flip back there so you can see this. So that's the shortcut. You won't have to do the Bohr diagrams after this next example, unless specifically requested. I'll pause for a second. Okay, we'll try another one. Fluorine. Well, fluorine's in the second row. So we're only going to use 2 of the rings. Across the first ring, 2 electrons. Then 1, 2, 3, 4, 5, 6, 7. And that makes sense because it's 17 is the column number, so 7 valence electrons. 2s, 5p. I'm going to put down the Bohr diagram. 7. 4, 5, 6, 7. For the actual Lewis diagram, I could have jumped straight to it. I'm only worried about the outside ring of electrons, and that's 7 valence electrons to put on here. 1, 2, 3, 4, 5, 6, 7. And that's a Lewis diagram. You'll notice that a complete row of valence electrons add up to 8 in general, but there's a couple of exceptions. They're the first one. The exceptions are hydrogen, just has 1, and then it could only have a max of 2 in level 1. And helium, we double it up right away because that's all that level 1 could have. The rest will generally have a 4-sided kind of diagram. When I say 4-sided, well, I think you can see that. I'll pause, but I'm going to ask you to copy down these notes here. Octet rule, what ions are, which you may be familiar with. Then I'm going to write down with you in a couple of minutes what cations are and what anions are. I'll leave you for a couple minutes to jot that down. So the octet, 8, octagon, you know, atoms tend to gain, lose, or share electrons in order to get a full set of 8 valence electrons. As mentioned before, hydrogen and helium are exceptions to the rule, and the transition metals don't follow this rule either. But we're going to deal with non-metals in the upper right-hand corner of the periodic table. They follow this rule for the most part. There's other exceptions, but not for high school with me. If you go into university, you'll see some things where you expand the octet, but I'm not worried about that. Ions are created when atoms gain or lose, when an atom gains or loses electrons. Now, the word cation and anion I tend to use a lot, and they're specific for the ions. So cation, oh, let's try this color. I'm colorblind, so I just choose colors. Kind of positive ions. They're positive ions, cations are positive ions, like sodium, Na+, because they lost electrons, you lose negatives. Anions are negative ions. And they're negative ions because they've gained electrons from their neutral state. An element will never gain or lose protons in a chemical reaction because that's a nuclear reaction, that's not chemistry. And if you gain or lose protons, you've changed which element it is. You have 6 protons, and you gain 1 proton to 7 protons. You're now nitrogen, a totally different element. So, chemistry is only gaining or losing electrons, and it's electrons that we're concerned with in chemistry. Okay? Cations and anions. I'll use those words quite a bit. I'm going to do this together with you. Predict the charge, give a Lewis diagram. All right. Sodium, I'm going to just flip to the periodic table. It's on the left side. Na, natrium, which is the Latin word for sodium. Anyways, there it is. As far as the valence electrons, it's in the first column. It has 1 electron, 1 valence electron that we're worried about. So its diagram is pretty simple. Sodium, Na, 1 electron. Now, the sodium ion is plus. I don't know if you guys talked in grade 9 and 10 about counting backwards to the closest noble gas, but sodium tends to lose 1 electron to be like neon because that's a complete shell. I'm not going to get into this too much, but the sodium ion is Na+. That must mean it lost an electron. So its diagram is just Na+, nothing on it, no electrons. It lost an electron to get a positive charge. Oxygen. Oh, son of a biscuit. Okay. Now, I'm specific because if I just say oxygen, I'm talking O2. So I say an atom of oxygen in the oxide ion. Oxygen is in the 16th column. It has 6 valence electrons. Same as sulfur and selenium below that. So here's an atom of oxygen. O, the 6th valence electron. 1, 2, 3, 4, 5, 6. Now, oxygen's closest noble gas is neon. It's 2 over. It needs to gain 2 electrons. If you look it up on a chart, oxygen has a 2 negative charge, negative 2 charge. The only way you can get a negative charge is by gaining electrons. To get 2 negative, you have to gain 2 electrons. So it's going to be, the diagram for it is going to be oxygen. Now, I'm going to use different colored pens. I'm going to just redraw what we have. And then I'm going to just change the color of the pen and say that we've added 2. You don't have to change the color, but just so that it emphasizes that. And then around this, we put a bracket, put 2 minus. If you put -2, like the negative sign in front of the 2 on 5. So that's either you pick up electrons, like in oxygen's case, it makes a negative charge, an anion. If you lose electrons, like sodium, you get a positive charge. Now, I am thinking, the 1046, we're going to just do this last bit on here and then we're going to call it a day, okay? Ionic compounds are formed between cations and anions. Usually these are metals and non-metals. The cations are the metals, the anions are the non-metals. Typically. There's some exceptions. We'll stick to the easy ones right now. We're going to predict the formula of the ionic compound sodium oxide. Now you're going to normally have an ion chart and do this way, but I'm using the sodium and the oxygen we just had. Okay? If you use the ion chart, which I gave you in your handout set, don't worry about scurrying around and finding it. You would see, and I just see this above. This is what it's like. We have sodium with a plus charge and oxygen with a 2 minus charge. So if I see sodium oxide, I look it up and I think, okay, Na plus, oxygen with a 2 minus, they combine to make a compound. You can probably see, and you'll probably remember from grade 10, you need as many positives as negatives to make a neutral ionic compound. That means, well, I've got +1 and 2 minus, I need a second group of sodium. Now I have as many positives as negatives. The formula that you would be expected to write down is Na2O. Get rid of that box. Okay? Now this should be a bit of review right there. Ionic compounds. I don't expect you to have remembered everything, but something you've seen. I want to show you this with valence electrons, though. So looking back at, sliding here, Na and O with their atoms, their neutral atoms, and they come together. I'm going to do it this way. I'm going to go with blue for the Na, two NAs. Now, I'm doing this on purpose. Single electron for this Na, single electron for this. Then, the oxygen. So those are the neutral atoms. When they encounter each other in a chemical reaction, if you just had sodium ions, or sodium and oxygen combined, you can probably see that there's a single guy there and there's a single guy there. Those singles mean that that's where, well, the electrons want to pair up to become more stable. We'll just leave it at that. It's a simple explanation. What does that mean? Well, the sodium will donate an electron to oxygen, and this other sodium will donate an electron to this oxygen. You now see that as a combined deal. I guess they've made each other happy. So I'm going to just go with, now you've got the two negative, you've got the plus, you've got the plus. That's where those charges come from. And they all come back to actually the electron configurations and so on. Now,